So guys, let's go now for the second part of lesson 6, which is titled Regression with Time Series Data, Cointegration, Deterministic Models, and Autocorrelation. I will start by discussing the concept of cointegration. Let's start by providing some definitions. First of all, a time series is said to be integrated of D order, or ID, if D is the minimum number of differences required to induce stationarity in mean. For example, if a time series is non-stationary and one difference is enough to induce stationarity, then the series would be I1. Sometimes several time series are individually ID, but there exists a linear combination which is integrated of lower order, ID minus m, for example. In this case, it is said that the series are cointegrated. As we will show in the example, a simple procedure to estimate a cointegration relationship consists in fitting a linear regression between the variables potentially cointegrated, and then evaluating the degree of integration of the residuals of this regression. In economics, the most common situation is that two series are I1 and their difference, exact or approximate, is I0. Cointegration between two series has two meanings. First of all, we can consider that there is a common trend component driving the series, so a combination of them cancels this component. Second, we can also understand that there is a long-term equilibrium between the series, such that deviations from this equilibrium show a mean reverting behavior. The figure shows the profile of the percent yield of long-term UK bonds. Long-term in this case means 20 years. And also the profile of the yields of short-term bonds. In this case, short-term means 3 months, 91 days exactly. These time series are quarterly, and the name of this dataset is UK Interest Rates EN-GDT. You can download it from the virtual campus. Both series show a directional trend, meaning that they tend to move upwards. And also, they are obviously non-stationary. To test for spurious correlation, we fit a regression between the corresponding first-order differences. So the dependent variable is D short, the explanatory variable is D long, and as we see, we have here a coefficient which is large, it is significant, and it is close to 1. The slope is significant, so the null that a trend-generated spurious correlation exists between these series is rejected. In this listing, we see the results of a regression between short as endogenous variable explained by long. So it is the same as the previous regression, but we are not differentiating the variables. We see that the coefficient of this regression is large, significant, and close to 1, as in the previous case. We also see that the residuals of this regression show a mean reverting behavior. So they go from below 0 to over 0, and then negative again, and then positive, and then negative, and then positive, and then negative. The mean of the residuals is 0, and these are reverting to the mean when they deviate. This means that both series, short and long, are cointegrated because a regression between them, which are I1, displays residuals which could be called I0, residuals which are stationary in the mean. If we rearrange the terms of this regression, we could move this coefficient times the variable long to the left-hand side of the equation. So short minus 0.999 long would be equal to minus 117 plus epsilon t hat. This means that this difference, which we call ZT, this would be a spread or a term premium, this difference would have a mean of minus 1.17. And this would imply that the short-term return is smaller than the long-term return. Smaller by how much? In average, by 1.17. and there is a deviation from this equilibrium. These deviations are displayed here. So the short-term bond may have returns far from the mean, both in the positive and negative sides, but they will converge to the mean, which will be minus 1.17. Now let's talk about deterministic models. We will discuss now how to capture trends and seasonal fluctuations by means of deterministic regressors, that is, variables that we devise to capture these non-stationary features. The starting point is the structural decomposition. The structural decomposition of yt is the sum of a trend component t sub t, the seasonal component s sub t, the cycle c sub t, plus an irregular component epsilon sub t. The trend captures persistent changes in the mean. The seasonal component captures periodic fluctuations in the mean, that is, fluctuations, changes in the mean, which cycle time and time again over the seasonal cycle. The irregular component has the standard properties of an error term, that is, it is zero mean, homoscedastic, and non-autocorrelated. And what is the cycle? The cycle is the rest of it. So that is the part of yt which is not assigned to the trend, seasonal, or irregular component. That is the cycle. We can also consider a fifth component, exogenous effects, if there are explanatory variables affecting the endogenous variable, for example, calendar effects. If the time series y sub t has been log transformed, then there will be an original variable y uppercase y sub t. Uppercase y sub t will be the exponential of y sub t, lowercase, and therefore the product of all these structural components. So, an additive structural decomposition in the terms of the logs of a variable becomes multiplicative in the terms of the original metrics of the variable. The simplest models for the trend are just regressions of the endogenous variable over a deterministic variable time. In this case, we see the log number of airline passengers fitted by a straight line over time. The equation given this straight line would be like this. Then the trend component, the blue line, would be a constant term plus an intercept times the variable t, and t is equal to 1, 2, n. So t is time. We could also want to fit the time series with a little curve, like the one shown in the second plot. In this case, the trend component would be alpha 0 plus alpha 1t plus alpha 2 time squared. These models would extract something that we call trend, but as we see, they fit badly the time series because there are other features that we may want to represent. Seasonality is a change in the mean which cycles over a fixed number of seasons that we denote by uppercase S. For quarterly data, S is equal to 4. For monthly data, S is equal to 12. A simple model for seasonality is a regression of the endogenous variable against 0-1 seasonal dummies. For example, in the case of the airline passenger series, we could relate the log of airline passengers with constant term, time, and time squared. This would be the model for the trend. It would be the trend component. And we could add to this regression this variable, and all these variables corresponding to the months of February, March, April, June, July, until December. Why are we omitting here the month of January? We are doing that because the variable underlying the constant term, which is a vector of ones, would be the sum of the 12 seasonal dummy variables. So we will have exact collinearity. When we are choosing the seasonal variable that we omit, we are choosing the baseline value. To illustrate this idea, for example, consider this coefficient here, the coefficient of dm6 corresponding to June. This coefficient is close to 20%. to 0.196, so that's 20% in terms of assembly elasticity. So what this coefficient is telling us is that if we are in June instead of being in January, we expect the number of airline passengers to be 20% larger. If instead of being in June, we are in July or in August, we would expect the number of airline passengers to be 30% more or less larger than the one corresponding to January. As you can see in the figure, the fit for the time series improved considerably over the model that only had a trend component. So now let's talk about autocorrelation from the classical point of view. In the next point, time series analysis, we will discuss the same issue, autocorrelation, from a more modern approach. Classical econometrics considers that autocorrelation is just an imperfection of the regression model, with the same consequences as heteroscedasticity. OLS estimates are therefore unbiased and consistent, but not efficient, and the standard inference results are not valid if there are autocorrelated errors. Therefore, the classical approach concentrates in detecting autocorrelation from the model residuals and, if required, in solving the problems that it creates, that is efficiency and inference. A classical test for autocorrelation is the one of Broich-Godfrey. This test the null of no autocorrelation against the alternative that the errors follow a PTF order autoregressive process. The value of P is chosen by the analyst, and the autoregressive process is this one. In it, we have epsilon t linearly related with epsilon t minus 1, epsilon t minus 2, epsilon t minus p. And this error here would be the non-autocorrelated error term. So, in a model with autocorrelation, we have autocorrelated errors, epsilon t, and non-autocorrelated errors, a sub t. The test statistic is computed on the basis of an auxiliary regression, as the white test that we saw in heteroscedasticity. Then we need to run a regression of epsilon t hat, that is the residuals from the main model that we are estimating, against the regressors of that model and against p lags of epsilon t hat with this error term here. Then we estimate this regression by OLS and obtain the corresponding R squared. The Broich-Godfrey statistic is n times this R squared, which under the rule of no autocorrelation is distributed as a chi-square with p degrees of freedom, being p the number of lags of the residuals that we are considering in the auxiliary regression. As you remember, a few slides ago I showed you a regression of the log number of airline passengers against time and time squared, with a constant term, and 11 dummy variables representing 11 months in the year. Now I am showing you the results of a regression of U hat against these same variables and 3 lags of U hat sub 1, sub 2, and sub 3. As you see, only the first lag of the residuals is significant. So we can say that U hat minus 1 is correlated or linearly related with U hat at time t. The statistic t times the R squared is very large, and therefore the p-value corresponding to this very large statistic is very small. Therefore, we are rejecting the null that there is no autocorrelation in the residual term, because the residual at time t is correlated with the previous residual. This would point to a first-order autoregressive model for the errors, and we would need to include this model into our analysis. Now let's discuss how can we include this consideration in the analysis. Modern econometrists consider that autocorrelated errors are not a problem by themselves. They are just a part of the model that needs to be estimated. According to this approach, we would need to estimate the regression model with autocorrelated errors epsilon sub t, and epsilon sub t would be this coefficient times epsilon sub t minus 1 plus a non-autocorrelated error. So the model would have two components. The relationship model relating the explanatory variables with the endogenous one, and the model for the error. This model has been estimated here. What we are doing is iterating over the value of the rho coefficient. Rho is equal to phi sub 1 in the notation of Gretel and in our notation. It is trying for different values of rho, computing the sum of squared residuals, and then stopping when this sum of squared residuals converges to a stable point. The value of rho, that is phi sub 1, on convergence is 0.67, and the values of the coefficients estimated according to this procedure are these ones. They are different, but close to them, OLS estimates with different standard errors. These estimates are efficient. These standard errors are supposed to be adequate, so the inference that we are doing with these p-values would be unbiased. As you can see, the R squared is pretty high, and the sum of the square residuals is pretty low. It is in fact smaller than the one in the OLS model because we added to the OLS model another component, the model for the error. So we are also forecasting not only the part of AT which depends on these variables, but we are also forecasting epsilon sub t as a function of its past. Even if we have some autocorrelations in the errors, OLS estimates have good properties, as they continue being unbiased and consistent. Therefore, a simple treatment for autocorrelation would consist in using Robustified standard errors. In this case, we are estimating again the model for the airline passenger series. These are the OLS estimates. They coincide with those in a previous slide. And these standard errors have been adjusted for autocorrelation, non-normality, and heteroscedasticity. This is noted by this message here. HAC means heteroscedasticity and autocorrelation consistent standard errors. When the sample is large, this procedure is rigorous and simple, as it combines consistent estimates for the parameters and their standard errors. So we get back the ability to test hypotheses that we have lost due to autocorrelation. The next section, time series analysis, deals with the modern approach to autocorrelation. As you can see here, this section will not be evaluated in the final exam, so I will not explain it. However, I advise you to review this material. Last, I will provide you some highlights about this lesson. In lesson 6.1, we saw that an effective way to deal with non-stationary data consisted in transforming it by differencing. This was an effective way to avoid spurious correlations. In this lesson, 6.2, we have seen that besides transforming the data, non-stationary can be treated in two alternative ways. First of all, by including in the model explanatory variables which are cointegrated with the endogenous one. Second, by including in the model also variables which are cointegrated but that we define, variables that we define to capture trending and seasonal non-stationarity. Besides the issues caused by non-stationarity, regression time series models often have autocorrelation in the errors. Traditional econometrics see autocorrelation as an imperfection of the model, which consequences are similar to those of heteroscedasticity. An easy way to implement a solution, very adequate for large samples, consists in computing standard errors robustified to autocorrelation, heteroscedasticity, and non-normality. A more modern approach would consist in modeling the autocorrelation as an additional element of the model. So, in the model, we will have two parts: the relation model, which will be a regression, and a model for the errors of the previous regression. And that's all for today. Thank you so much. Good night and good luck.